Okay. So I'm going to talk about COLO, and COLO is a project around high availability and trying to give a high available solution for VMs where you have workloads or applications that you would like to have highly available, but you don't really want to go in and muck with them too much. I'll start off by just talking about some basics around high availability, what that is, and what it means to be highly available. Look at a client application that that we'll use to as an example for how you make something highly available, and then look at a couple different ways that we can apply this, to a cluster using Remus, COLO, and then get into more of the COLO architecture and foundation, and then a little bit of performance, and then the current status. The high availability is mostly trying to get rid of a lot of the single points of failure, places where you might have some hardware. This is all hardware. Software problems, those are going to be there, but they're not fixed by this. So you have a problem with your server going down, your power going out, storage going bad, things like that. That's the kind of thing that we're trying to avoid here. And mostly we avoid those by replicating them. We just make multiple copies that we can use in case one goes down. We can kind of move or be operating on the other. And then the definition of availability here is the total time minus your downtime and all of that over the total time. So, this is just as an example here. I pulled some data off the network, and this is hosting data from 2005. Actually, I don't know if you can see it, but right here, that column there is the availability number that we just looked at, the definition for. And most of the data there is in the 2 nines case. There's one outlier that doesn't make 2 nines, and then there is one that makes 3 nines. And here I've graphed the data where the red is the availability actually it's not availability, it's downtime for the blue dot, its corresponding blue dot, which is the availability. So the higher the availability, this is the closer to 1 that number is, the less downtime you'll have. And the way we usually talk about that is nines. So 2 nines of availability is about 7 hours of downtime a year. A month. And then as you go up, you get 3 nines, you're below an hour. And then it takes almost to 4 nines to where you're down to an hour a year of downtime. So the client server app that we want to look at here, it's just going to be a web store, and running the LAMP stack that we talked about earlier today, and then a custom store that sits on top of that. And you can see that there's just, it's Linux, you've got Apache, PHP, MySQL, and then your custom store. All that runs on a single server in general, and the server's connected to the internet, so you talk to clients. So to make that particular case highly available, what we do normally is we just bring in a second server. We would connect them with 2 separate network interfaces, so that if one of those goes down, we've got it. We would, in this case, we're synchronizing our disk across the server so that we get the same data on both disks. This is important for MySQL. We don't want to lose data when we're when we take an outage. We don't really want to have to rebuild. Then by doing all that, if one server goes down, it's okay, yeah. If one server goes down, then we can, we can just switch over to the second server. And that switching and the communication between these, this is in the clustering and the pacemaker layers there. It's a second and third layer. That's where all of the magic here is done, other than the synchronization of the disk, which is in the fourth layer there. Everything else is just the app. Now, if we want to do that with VMs, and that's mostly what we're talking about here, it's almost exactly the same situation. So we've got all the software, the stack, running inside of the VM. This is DOM-U in this case. And so you can see we've just got the Linux, the clustering, pacemaker, DRBD, and then our lamp, the rest of the lamp stack is there. All within the VM. Replicate those VMs across our servers. So we still have the dual servers, we still have the dual storage, networking, to make everything, anyway, to make everything work there. So very similar to, with virtualization and without. However, we might have a situation where we are back at the original base, a single server. We've got our application running within a VM, and if that's the starting state, then we may not want to go in and put in our clustering software, pacemaker, and all of that into our VM. We've got that tuned, and we just don't want to mess with it. So a way to work in that situation is to use some special sauce. Actually, I think I've got that on the next slide. But so here we're trying to separate out the application development versus the HA so that they're not intermingled. So here we, again, replicate the servers, the network. We switched over to a SAN. This is just because the software deals with a SAN here, our special sauce. And other than that, the software stack that's in the DOM-U there is the same as our original server software. So it's just Linux, it's the LAMP stack with the custom store. Now, for this to work, what we need is the special sauce to ensure that we are up to date on the secondary, so that the two VMs really have the same state, or an equivalent of that. And so we have the replicated machines and network and all of that, but we need something to do the VM sync and to watch for failover. And that's where this kind of the sauce comes in. Now there are two possible places where you can get the sauce. One is in around Xen. One is Remus, and the other one's COLO, which is the main part of this talk. But Remus really came first, and it was the spark that brought out COLO. So Remus was a project at the University of British Columbia, and what it does to make the HA happen is it uses the two servers, keeps the secondary as a kind of a pre-launch live migration. So it's not running there. It just kind of sits there, but it's staying up to date and it's like doing a live migration, but just just stopping before you turn it on. And so the way Remus works is it will handle things in an epoch, so a certain amount of time. It receives the requests that come in, and it will answer the request, but it buffers the output from the server. And as it buffers that up, it collects all the state that it can release at the end of the epoch. Before it releases it, it syncs with the secondary machine, and then after it's done syncing, so the state's the same on both sides, then it releases the responses to the clients. And then it repeats this through the cycle. So at every point where data's gone back to the client, the two machines are in 100% equivalence state. Now, some of the overhead that causes is that you have the actual latency of the requests that normally would happen if you were a native system without this. And then you've got about a half of the epoch that, where you're just waiting to respond. And the epoch is adjustable, so it really depends on what you set it up to be. 20 milliseconds, 40 milliseconds, that's all in, in the ballpark of where you might run it. Then the other overhead here is the checkpointing time. And really, you're just copying the memory storage, the network interface information that you need to. And the overhead, if you're doing that 10 times a second, is about 31%. This is out of their paper. If you do that 40 times a second, so that's 4 times more stuff, then you end up with about 100% overhead. And so you really try to balance that for your application. Now, COLO is a little bit different. The reason that we call it coarse-grain lock-stepping is the object that we're using to do the stepping is the response. So we run 2 active systems instead of the active-passive. They both receive the request, operate on the request, generate a response, and then that response is checked. So if it's equivalent response, then we release one to the client, and that's if it's not, then that's the point that we have to do a checkpoint. So that's why we call it coarse grain. The grain is the size of these failure to match. So then we do a full checkpoint just like Remus would do, except that we actually start the start the secondary VM, and then the reason that this has an advantage over Remus is that the rate of these checkpoints generally is lower because of the mismatches, more seldom than the time that we would specify for an epoch. And to look a little bit closer at the architecture, what we have is 2 systems here. On one side, we've got the primary machine, and of course, both machines are running DOM0 and then our application VM. And they each have their own copy of Zen, so it's all replicated there. Within DOM0, we have the heartbeat and the checkpointing mechanism, and then COLO Manager, which is that does the comparison of the output and triggers the checkpoint, does some optimization things. So this I can't even read it because of the size, but The key things here to see is that the way that in the background, this is just an optimization basically, but the way that the system works is as the primary is going along, occasionally it will look to see what pages are dirty, and it'll send those over to the secondary. This is all just getting ready so that when there is a checkpoint, it will have less data to transfer at that time. So it's just pre-staging some of the dirty pages that would need to be done at a checkpoint. This is most important when the checkpoints are happening very seldom. So you build up a lot of mismatched state over time. This helps to alleviate that. Then in the way the storage works, storage is also a kind of a problem here, because at a failover, we don't want to try to back out anything that's on the disk of the target machine. So the writes from the primary machine go both to the primary machine's disk as well as to a cache that's stored on the secondary machine. And then when it does a read, it just reads off of its disk. The secondary machine, when it writes also to a cache, but it's the secondary's cache. So neither of these are going to the secondary disk. And when the secondary reads, it checks the cache first, and then it'll go to the disk. And that way, we don't mess with the data on the secondary disk. It matches the start of the last checkpoint from the primary. Now, when there is a checkpoint that occurs, the data from the primary's cache is written to the storage, so that brings it up to date. If there's a failover that occurs, then the secondary's cache is written, and that way, because we're going to start treating this as the primary, so we write that, then we're all up to date, and the secondary turns into the primary and moves forward. So the overhead, this is very similar to the overhead that we talked about for Remus. The overhead we have around latency, but in this case it won't be as bad. Here we take the slower of the two applications, whichever VM is running slower. We take that time plus the amount of time it takes to do the comparison, and that forms the latency for the request. But every request, goes through that comparison, and then it's sent to the client. So we don't have to buffer it beyond that. And then there's the checkpointing overhead that goes on. Now, this generally will be not as bad as what we would see in COLO. In Remus. And a big part of this is because the two machines are moving forward. They're both generating state. And one of the issues here is that because they can be multi-threaded, these are non-deterministic. So the two VMs will get out of state, out of equivalent state. And so that generates different, a different sequence of responses that you would get. In fact, a lot of the responses and the things that allow us to optimize it are that the responses are things like timestamps that are on the network packets. Those things are not true application differences, and so they're just a matter of optimization. But the application itself can be different in the response. You could get requests for allocating some resource that would come in, and the two different VMs may allocate those resources to different customers. So once that's detected, then that triggers the checkpoint, And at that point, that's where we take the overhead here. So if some workloads are going to be more likely to have those kind of differences than others, and that really generates the rate. So some workloads, if it's compute intensive, will tend not to have these checkpoints. Other workloads will have a lot of checkpoints, and some can be worse than Remus in terms of the rate. Actually, this next section is a little bit hard, but so we're based on just the foundation of full checkpointing. This is like hibernation or live migration, and that's the assumption for going forward. To have an equivalency, but that's actually stronger than we need, as we were just talking about in terms of the client sequence that it gets what the response is. The customers only care that they get a valid sequence. They don't really care that the state of the machine is exactly the same. So as long as the sequence that comes out of the server, and whether it's a single server or it's a high availability server, if that sequence is valid, then you're good. And so as long as when we're in the high availability case, we have a sequence that goes from the primary node to the failover secondary node, that sequence is still a valid sequence, then we're okay. And in that case, the client would be happy. In COLO, the secondary is running the application all along. So it's the sequence that leads up to the failure is a valid sequence, and as it continues through the failure, it continues to be a valid sequence. So that's really the heart of what makes COLO work. Is that, that's the linchpin. And we can go through it in a more formal way. That's what's on this page, and I think the next page. But essentially, it's just kind of showing that the sequence, as we do the failover, is a valid sequence. All assuming that since they're both running the application on both nodes, that's what causes it to be valid. So. I'm not sure people wanted to go through that, but so why do we care? We care because by allowing us to kind of ignore some of the exact state and move to the sequences, we can have fewer checkpointing and get better performance. So we did some work on some benchmarking with Pgbench, and then some database stuff next. Now, this is all in the paper, but here we're judging the performance by the throughput, and we look at a set. There's several sets here of data that we look at as we're increasing the client thread count as they're banging on the web server. Within each set, the first bar is the native performance. Then we've got the Remus performance at 20 millisecond epochs, 40 millisecond, and then the COLO performance. So in this first set, you see that COLO is just about native performance, and it's quite a bit higher than the Remus performance. Second set, very similar in the third set, but COLO is starting to fall, and then COLO falls across the next three sets. Still remains better than Remus, but The fall here is caused by having lots of streams coming in across the network, and our optimizations haven't quite figured out how to hold those different streams and to do the right compares. Sometimes we're comparing different streams when we should be, we just have the wrong the wrong result packets that we're comparing. So there's some more performance work to be done to raise those, but it still is performing better than Remus, and it's not doing too badly. Still with Pgbench, when we look at the MP scaling, so this isn't huge scaling, it's just 1, 2, and 4 processors, and we're comparing against native. So we've got COLO performance against native, and when there's just one client thread requesting data, we're almost right at native performance. When there's 4 threads from the clients, we're virtually at native performance, and then it starts to drop as we add 16 threads from the clients and so on. And this is, again, all about the packet compare, and having lots of threads, it's harder to keep track. But across each set here, so going from 1P, 2P, 4P, it scales very well. It's just about the same. Now, when we look at the benchmark case, here we've got throughput is the performance measure, and then we've got our sets of native, the 2 Remus, and COLO. And in this case, again, COLO's performing pretty closely to native, and better than Remus. Pretty much across the board, we see the same pattern as you go up in the number of client threads. And then with the CPU scaling, we've got 1, 2, and 4 processors. And here, each one of those sets is pretty close to each other. The first one is is kind of the strangest, but they're pretty close. So the current status, actually, here I wrote that I thought COLO was going to be in 4.5. There's some changes going in for Remus. Those changes for Remus may make it in. Looks like from the discussion with Conrad that maybe the COLO work won't make it into 4.5, but we'll see. It's coming down to the wire. And then there's a paper here that was in the ACM symposium last year, and that's it. Are there any questions or?
What's the maximum number of servers on this cluster?
Well, this is just it's just active passive for Remus, is active for COLO, but it's just the 2, so there's no fencing that you can do here.
When you have processors, you mean 4?
Yeah, processor. Yes. Actually, I think that's yes, but it may be sockets, and I think in this case they're probably the same thing, cores and sockets, but yeah. I'm sorry if my answer is confusing, but. There are a couple talks we've done. We presented at the Zen User Summit in 2012, and then in 2013. The paper, and then there's some, of course, code that's been pushed upstream. So this code is on the mailing list, right? It's not part of the release yet. Also, there's some work that's probably, it's more new. It's about a year old, that's starting to go for putting this stuff into KVM as well. And I just saw within a few months ago that the initial work was pushed into chemo. So
Is it the source license like GPL?
yeah, well, this stuff is set up to go into Zen, so it's, you know, for the Zen side of it, it's just the same as Zen. Any other? Okay, thanks.